Let's have a look at the next problem. If the earth were to spin faster than the acceleration due to gravity at the poles, options A increases, B decreases, C remains constant, and D depends on how fast it spins. Dear students, this problem is based on the variation of the value of g, acceleration due to gravity, due to the angular velocity of earth, that is due to the omega of earth about its own axis. And we need to know the expression for the variation of g. G varies with omega according to the expression g dash is equal to g minus omega square r into cos square lambda. Students should know that the value of lambda is 0 degree at equator, and at poles the value of lambda is 90 degree. Since the problem is based on the value of g at poles, value of lambda at poles is 90 degree. So what happens to g dash? Cos 90 is 0. The value of g dash is g, which is maximum at poles. Students are supposed to know the value of g at poles. The question is, if g dash is g at poles, then how does omega affect the value of g? Since there is no term called omega in the expression for g dash at poles, obviously omega has got no effect on the value of g at poles. So the answer should be obviously g remains constant, or in other words, g doesn't depend on the speed of rotation of earth. Remember, this is true only for poles. But if the same question is asked for equator, what's the value of g or g dash at equator? At equator, lambda will be 0, and the expression for g dash will be g dash is equal to g minus omega square r. Let me write the expression. At equator, g dash is equal to g minus omega square r. Now what happens if earth stops rotating? Omega is 0. Omega is 0 when earth stops rotating. The value of g dash reduces to g. Now what is the change in g? Earlier it was g minus omega square r. Now it is g. So what has happened to the value? Obviously it has increased. How much? Increased by omega square r. I repeat, when earth stops rotating, the value of g increases by omega square r. This is also one of the most probable questions. Similarly, if the same question is asked for other than equator or poles, you have to go back to the same expression. Here, if earth stops rotating, put omega is equal to 0, the value g minus omega square r cos square lambda reduces to g dash is equal to g. Now what is the change in g? G has increased by this quantity, omega square r cos square lambda. This is also a probable question. Ultimately, students concentrate here. When earth increases its velocity, when earth spins faster, if omega increases, g should decrease. If earth stops rotating, or if earth reduces its velocity, if omega decreases, value of g increases. Have a look at the next problem, dear students. A satellite is orbiting around Earth. By what percentage should we increase its velocity so as to enable it to escape away from Earth? Options: A 41.4%, B 50%, C 82.8%, and D 100%. Dear students, to solve this problem, we need to have the idea of expressions for orbital velocity and escape velocity. Orbital velocity is given by the expression VO is equal to root of GR, VE is equal to root of 2GR. Now, the satellite is already orbiting around Earth. In order to make sure that the satellite escapes away from the Earth, you need to give a velocity to the satellite so that its velocity becomes equal to escape velocity. Now, when you provide velocity to the satellite, what is the change in velocity and what is the percentage change in velocity of the satellite? That's what you are supposed to find. Obviously, change in velocity is final velocity minus initial velocity, that is final velocity is escape velocity, initial velocity is orbital velocity. So, change in velocity is escape velocity minus orbital velocity, whereas percentage change is change in velocity divided by original velocity into 100. I repeat, percentage change is change in velocity, that is VE minus VO divided by original velocity is VO into 100. So, what is VE? Root 2 GR. What is VO? Root GR divided by original velocity is root GR into 100. So, this comes out to be, I think root GR is common, gets cancelled with the denominator, and we are left with only root 2 minus 1, that is 1.414 minus 1 is 0.414. When multiplied by 100, the value will be in percentage. So, this is root 2 minus 1 by 1 into 100. This is 1.414 minus 1 into 100. This is 41.4%. Option A is the correct answer. Dear students, let's take up a problem which is based on Kepler's laws of planetary motion. The problem is like this. When Earth moves around the Sun, the quantity which remains constant is options: A. Angular velocity, B. Kinetic energy, C. Potential energy, and D. Aerial velocity. Dear students, this problem is based on Kepler's second law of planetary motion, which says that the imaginary line drawn from Sun to the planet sweeps out equal areas in equal intervals of time, which clearly says that the aerial velocity is constant. Obviously, the answer is D. The correct answer is D, aerial velocity. But let's have a look at the other three options also. When it comes to the angular velocity, we also know that when the planet revolves around the Sun, the radius vector, the imaginary line drawn from the Sun to the planet, doesn't cover equal angles in equal intervals of time. It only covers equal areas in equal intervals of time, which means omega, that is the angular velocity, is not a constant. I repeat, any planet will not revolve around the Sun with a constant velocity or not with a constant speed. So, since the speed changes, its kinetic energy also changes. Coming to potential energy, the planet maintains different distances from the Sun at different positions along its orbit. Therefore, the potential energy also keeps on changing from place to place. So, these three parameters keep changing when the planet, or Earth in this case, revolves around the Sun, whereas the aerial velocity remains constant according to second law of Kepler. Dear students, now let us discuss some of the very important concepts and questions from oscillations. The chapter oscillation starts with simple harmonic motion, which is the simplest kind of oscillation. The motion is said to be simple harmonic motion or SHM, provided two conditions are satisfied. Condition number one is the acceleration of the particle is directly proportional to its displacement. Condition number two is acceleration is always opposite to displacement. This can be expressed in terms of symbols, that is acceleration is directly proportional to y and acceleration is opposite to y, that is a is proportional to minus y. And the displacement of particle at any instant of time is given by the equation y is equal to a sin omega t. Here capital A indicates amplitude and small a in the expression of definition of SHM indicates acceleration. Now, the velocity of the particle at any instant of time can be obtained by differentiating the displacement equation, that is v is equal to a omega cos omega t. This can also be expressed in terms of displacement. I repeat, v can be expressed in terms of y as well as in terms of t. In terms of y, that is displacement, it is v is equal to omega into root of a square minus y square. And coming to acceleration, if you want to get the expression for acceleration, differentiate velocity again, you will get a is equal to minus omega square a sin omega t, which can also be written as a is equal to minus omega square y. Students should remember the values of velocity and acceleration at two very important positions of the body or executing SHM, and those two positions are number one mean position, number two extreme positions. So to remember this, you have to make a table like this, which says that the displacement of the body is 0 at its mean position, which is minimum, and at extreme displacement is maximum given by amplitude, that is plus or minus a. And when it comes to velocity, it is maximum at the mean position, which is given by plus or minus a omega, and 0 at the extreme position. And acceleration, however, it should be same as or directly proportional to the displacement. Therefore, acceleration will be 0 at mean position and maximum at extreme position, whose magnitude is omega square a. Now, angular velocity of a particle executing SHM is given by the expression omega is equal to 2 pi by t, where t is time period of oscillation, which is given by 2 pi by omega. From the expression of acceleration, that is a is equal to omega square y, we get an expression for omega as root of a by y, that is omega is equal to acceleration by displacement. T is equal to 2 pi into reciprocal of omega, that is t is equal to 2 pi into root of displacement by acceleration. The same expression is used in the expression of time period of simple pendulum, that is time period of simple pendulum is given by t is equal to 2 pi into displacement by acceleration, that is root of L by g. And very famous question, time period of simple pendulum is what happens to the time period of a simple pendulum when length of the pendulum is increased by x%. Students can use a shortcut here. If the length of the pendulum is increased by x%, then its time period also increases by x by 2%. Similarly, t can also be changed by changing g. If g is reduced, t increases. Similarly, if g is reduced by y%, then time period is increased by again y by 2%. Remember that by 2 factor is because of this square root. Now, some problems can also be asked based on loaded spring. Omega for loaded spring is given by omega is equal to root of k by m, where k is force constant. Now, that is why we can write an expression for time period, that is 2 pi by omega, which is t is equal to 2 pi into reciprocal of omega, that is m by k under root. Very famous expression. Now, what is more important in springs as far as competitive exams are concerned is they do combine 2 or more springs in series or in parallel, and you have to find out the effective force constant of the spring and you have to substitute in this expression. Single spring, then no problem, no worries, you can substitute the value of force constant here and get its time period. But if two or more springs are connected either in series or in parallel, the expression for time period changes as K effective changes. The effective value of K is given. When the springs are connected in series, then effective spring constant or force constant is given by 1 over Ks is equal to 1 over K1 plus 1 over K2 plus 1 over K3 plus so on up to 1 over Kn. If there are only two springs, you can easily write Ks as K1 K2 divided by K1 plus K2. This is the expression when two springs are used. Now, if the springs are connected in parallel, then effective spring constant is Kp is given by K1 plus K2 plus so on up to Kn.